Okay, good evening everyone. Nice to meet you all here. Do you hear me? Everything is fine with connection?
Yeah, we can hear and see you well.
Okay, thank you. That's great. So, my name is Timchishin Vitaly, and I guess for the next few months, I'll be your guide into the exciting realm of bioorganic chemistry. Um, so we will have, I guess, something like 15 lectures, and I have split them into three parts. So the first part is basically more chemical, so it's some sort of mixture between physics and chemistry. The next five lectures will be something that is more commonly called as the biochemistry, and the last part, I guess, that will be something that you can call functional biochemistry or something in between biochemistry and physiology. This course, let's say I'm still creating this on the go, so please do not hesitate to give any feedback, so I can take into account what you want and how it's going for you. Okay, so with that being said, let's try sharing screen. Okay. Mhm. Okay, so let's start. The first lecture is about what may be a bit of surprise for you about quantum mechanics. Why quantum mechanics? The thing is that, first of all, everything you see around is basically a result of quantum mechanics. Chemical bonds are quantum mechanical effects. So you cannot get any chemical bond if you don't take quantum mechanics into account. Solid bodies, they cannot exist in the classical world. So system of charges is unstable due to the Earnshaw's theorem. So if you have just number of charges, you can think about, I don't know, sodium chloride, for example. So you have sodium ions, you have chloride ions, and we all draw that like a nice crystal, but that crystal cannot exist in the classical world, so you need quantum mechanics to exist. Moreover, some tunneling effects are observed for enzyme catalysis. So I have put a link here for you. You can check, there are much more links, and there is some sort of debate going around. But anyway, I wanted to know that even in such things like catalysis by enzymes, quantum mechanics can, well, has some role. Uh, okay, I'll try to give it to you without any equations, so just basing in some, let's say, hand-waving way. But I think that should be enough for you to get some general idea about chemical bonds and basically what what I would like you to show and to understand. First of all, a small thing. So what was before quantum mechanics? That was 19th century, and everyone thought that light was just waves in ether, and particles were tiny balls that respect Newton's laws. Uh, but then this picture started crumbling. And here I want to show you one of the experiments that may be more or less intuitive for you and that demonstrates why do we need quantum mechanics. Here is some excerpt from the video. I guess it's Action Lab channel. And here you see a device called an electroscope. And you see that this guy is charging the device. He's putting negative charge on this plate. This charge is distributed through the device. It's called an electroscope. And you see this tiny arrow, and this arrow, as you see, changes its position. Why it does so? Because everything is metal. Charges are distributed throughout the device, and you know that like charges, they do what? They are repelling each other. So the tip of the arrow would be repelled from this column. Okay, now what's next? The thing is that when this device is charged, we might think, what can we do to discharge it? So maybe we would like to knock off some electrons from this plate. What should we do for that? To do that, we will try to shine light. So light carries some energy, and we think that this energy, if we transfer that energy to the electron, it might have enough energy to leave the plate and to go somewhere in space. Now look what happens. Well, nothing happens. That's a really bright flashlight. So we are putting enough effort to knock off that electrons, but nothing happens. That's quite interesting. You might think that we just didn't have enough energy to knock off an electron from that plate. But let's take a look at different experiment. Here you see a UV light. It barely shines some light, so it's really safe to handle and so nothing special. But now look what happens to the device. Look at the tip of the arrow. So now you see that electrons are leaving the plate and device is discharged. This is called basically the photoelectric effect, and that's the thing that brought to Albert Einstein his Nobel Prize. So probably you might think that he got his Nobel Prize for the theory of relativity. No, he got it for this sort of effect. And he explained this effect in such a way. He told, well, we should think about the light not as a wave, but like some tiny particles called photons. And each photon has some energy. And the question of knocking off the electron from the plate is basically the question of colliding an electron and a photon. They are colliding. So this is the question of the energy of one photon, not the population of photons, but just one of them. And each photon has energy defined by the wavelength. So you can use really dim light, but if it has very small wavelength, each photon will be quite energetic and it will be able to remove an electron from the plate. So here is the place when we started to think about light like particles. Here is a tricky question for you, I guess. Let's charge the electroscope with a different kind of charge. So we just have charged it negatively. Let's charge it positively. Okay, so you see we can charge an electroscope positively. And now I want to ask you a really tricky question. What would happen if I shine once again the UV light on this device? Who can tell me? What do you expect?
Can you repeat the question one more time, please? About shining or what exactly?
So we have electroscope. Now it's charged positively. So before it was charged negatively, now positively. And now I'm shining UV light on the electroscope. Previously you saw that electroscope was discharging. What would happen now? Does it change anything that I have charged it not negative but positive?
There is kind of influence of energy. It means that energy just will be going in another state.
Maybe it will turn in another direction.
Maybe photons from light source will neutralize electrons.
Yeah, maybe it's gonna stop.
Okay, let's start with a bit more simple question. What does it mean to have positive charge for this device? What did I do to this device to make it positive?
You remove the electrons from
Yes.
its atoms.
Yes, I have already removed electrons from the device, so it is charged positively. So if I will shine some light trying to remove some more, I probably will not succeed, unless this is a really some powerful device. So right now you can see that nothing happens. So let's check it out now.
So you can see that nothing happens.
Okay, so we have already removed electrons, and photons, they haven't enough electrons to knock off this plate. Okay, so that was the first part. So we thought about light like waves before, and now we start thinking of it like particles. That's okay. But there is another experiment that basically makes us think about particles, or whatever we considered as particles before, as having some wave properties. And this is a well-known double-slit experiment. So here you see a beam of particles, and here you see this double slit. So one slit and another. And what we would expect in a classical world to see on the screen, so here is the screen, and here you see this screen, let's say, like turned on its side, so that we can see the image. So what happens on that screen? So these dots are, let's say, some positions that we would expect to see particles. If these are some classical balls, well, that's pretty okay. So that's what we expect. But if we have a beam of particles that are, let's say, tiny quantum particles, some electrons, protons, we will have a very different picture that looks like this. And this strange result, there were these two gentlemen, Davison and Germer, that conducted the Davison-Germer experiment, and this is the experiment in which electrons are scattered by the surface of a crystal of nickel metal, and they displayed a diffraction pattern. And that was very strange. So this was a confirmation of the hypothesis of wave-particle duality. So here I want to show you a screen, and each dot is basically an electron touching this screen. These electrons, before getting to this screen, they have passed that double slit. So what I want you to notice, first of all, each electron gives you one dot. So it's not like one electron gives you, I don't know, some wave pattern. So no, it's not. It gives you just one dot on screen. But if you take many electrons and you send them through this device one by one, you will get one dot, another dot, another dot, another, so many dots. And you will see that these dots have a very interesting pattern that does not look like two stripes. It looks like many stripes. It looks like some interference pattern. So that's what we know. So we know that particles have some sort of wave properties. And this was a crucial moment. So at some point we understood that everything we know about our classical world is not applicable. Oh, I see. Is there a question? Okay, somebody shared a link, so that's great. Please look. So at some point we understood that we should describe quantum particles pretty differently. So if we describe a classical particle with some sort of position, maybe velocity it has, we should describe quantum particles pretty different. And the different approach that we take right now is the wave function approach. So we describe each particle with the function defined in the whole space. I want to show you some sort of classical analogy of this wave function, just to create, I don't know, some simple image in your mind. What should it be? So here is an experiment with a rope, and you see standing waves in the rope. So here we have it. What I want you to think of, well, you might think of this experiment as some sort of analogy of a particle being confined in a potential well. This rope represents the wave function that describes the particle. So it doesn't really exist, yeah, because I don't know, that's abstract mathematical things. So mathematical things, they do not exist in reality. But that's something that we use to describe the particle. You see that it is wobbling, so that's why we call it wave function. Of course, there are some more reasons, because it comes from the Schrödinger equation, and basically if you solve that you will see where does this all come from, but I do not want you to get into that equations because it's a bit too complicated. But I want you to see that with each particle you can associate something that is, let's say, wobbling and is defined in a space, at least where it is reasonable to expect for the particle. One more thing, this wave function not only describes the particle, it brings us some useful information. So if you see, let's check it. How do I do this? Yes, right. Let's check the central part of the rope. So you see that the rope is wobbling here quite significantly. The amplitude of this wobbling defines the probability of finding our particle at that point in space. So basically, where the rope is wobbling the most, it's like it's the place where you expect to find your particle most of the time, or it has the biggest probability of you finding that there the particle. Wave function may have nodes. So these are places where no wobbling is seen. This means that the amplitude is zero there, and since this amplitude is zero, there is zero probability of finding their particle. Let's check a few more examples, because what I want you to see is different ways a rope can wobble. Here you see we can have one node in the center of the rope. Oh, I see a question. Yes, please.
So basically, we can say that on the first example, we have one square. If we put the square on the middle of this rope, we'll have one square. We'll see the result of this wobbling. And in the second, we will see like if we have like two squares, we'll see that the two squares will have the most appropriate ways that explain us where it can be.
Yeah, so
right?
you will expect, if you measure where is the particle, you will expect to find it somewhere here or somewhere here. But you will definitely not expect it to find somewhere in here, where we have small amplitude. And we will see that this analogy propagates later to orbitals. So we will talk about atomic and molecular orbitals, and you will see that this analogy still works there. It's somewhat hand-waving, but I guess it should be okay. So one more mode So now you see here three parts of the rope are wobbling. You see two nodes, and what I want you to notice that the more nodes we have, the more vigorously we should shake this rope. So more nodes means we need more energy. We need to put into there more energy. And you will see that this analogy still works in case of atomic orbitals. Here is that equation I told you about. So time-dependent Schrödinger equation. It is really hard to solve. I guess the best we can get analytically is hydrogen atom. So anything else, even helium atom, there are certain problems. So basically people are working to get some approximate solutions to the Schrödinger equations. Equation, and if you heard about, I don't know, density functional theory, for example, or some perturbance theory and so on, that's all the methods to make something with this equation and get some approximate result. And basically you can make a whole career in physics just by finding some good methods of solving this equation, at least in some cases. Here I just wanted to show you, first of all, this is the hydrogen atom and it's his wave function. You can probably look here and see that it looks pretty complicated. It already contains special functions, so some Laguerre polynomials and some spherical harmonics, so it's really complicated, and I don't expect you to know how that works. Just see that it's complicated. But on these images you can see basically this wave function, and you see the nodes of this wave function. We will have some better images later in the lecture, but I just want you to see that there are some bright spots. So here is a big probability of finding the particle. Well, actually an electron. It's all calculated for an electron in the hydrogen atom. And there are some nodes, so dark places, where you will not find that electron, or there is a really small probability. Here is an example how we transform the wave function into the probability distribution. You see two curves here because the Schrödinger equation, it supposes that wave function is complex. So this is real and imaginary parts. Yeah, non-exact or solved numerically, yes. So basically solving Schrödinger equation numerically, you can make career as well. So it's really a decent problem, and we really need that in many cases. So I don't want you to, well, to be too obsessed with these functions, but just to see that from the function we can get probability. Okay, but now of course you can ask me, why don't we just describe our particle with some sort of probability distribution? So what is there so interesting that we need a wave function? And the thing is that wave function can interfere, and they can interfere, for example, constructively, given some bigger waves, or destructively, giving zero. So unlike classical mechanics, we describe particle with this psi function. We know that it's somehow oscillates. These oscillations, they may interfere constructively or destructively, and the end result you get, if you calculate this absolute value squared of the psi function, you get the probability of finding a particle somewhere there. And here is an interesting experiment that demonstrates that interference and gives you some feeling how strange can be the result that you get. Let's take a look. So it is called Mach-Zehnder interferometer, and what do we have here? We have a laser that shoots some photons. We have a beam splitter. This device, it basically quite a simple device. What it does, there is 50% chance that photon will pass through this device, or 50% chance that it will go sideways. So 50% here, or 50% here. So nothing special. Same beam splitter here. What's interesting, you see that when photon is reflected from something, it gains some phase change, let's say 90 degrees. So the thing is that when a photon comes here and just passes through, it does not gain any phase, so it's 0 degrees. If it is reflected, it gains 90 degrees. Now photon is reflected here, so it gets phase 180 degrees. This one is reflected here, it gains 90 degrees. Now the very interesting thing happens. So the second beam splitter, it mixes wave functions from photon coming through this path and this path. And the thing is that if this photon reflects here, it gets 180 degrees phase change. So we have 180 degrees and 180 degrees. If he passes through, but this photon is reflected, we get 270, that is minus 90 degrees, so minus 90 degrees, and we have plus 90 degrees. Okay, you may wonder what am I calculating all this way, but what I want you to show. Look here, when we are combining photons that have the same phase shift, we are basically combining them in phase. So I have wave function that goes like this, and I have another wave function that goes like this. They are doing what? They are constructively interfering, so at the end I get some larger wave function. So there is a high probability of getting through. Now look at the second case. I have one that is shifted 90 degrees, so it's something like this, and I have another one that is shifted minus 90 degrees, so it's something like this. If I add them together, they will interfere destructively, and I get nothing. So here what I want you to show, if I send a photon from this laser, there is a probability 1 to get it from this side of the interferometer, and probability 0 to get it from this side. If it's not enough strange for you, I want you to think about this case. Here is the same interferometer, but I have blocked one of the passages. Now there is 50% chance to get here, and then 1/4 to get here or here. And now is the tricky question. If I get a photon here, what does it mean? What interesting information did it brought to me?
So as you mentioned, we will have like 90 if we go down, and then 90 to the mirror before 1.25. And then if we go down, we'll have like the string, the stray light, as you mentioned, or it will be like what?
Look, we have blocked one of the paths, so you can't get interference here because here is blocked.
So yeah, we go down like 90 degrees down, and then 180 degrees.
Well, it's not
right?
it's much simpler problem. So in previous case, when I had two paths for the photon, so he could go either down or up. what was the probability to get it here?
0.
0. So now if I block this path, I start getting some
The
photons.
probability is a quarter.
Yeah, so there is a quarter probability, but if I sent a photon and if I got it in this sensor, that means that this passage is blocked. So he brought me information that one of the paths is blocked. But now think about it.
Okay.
How does it know that that path is blocked? If he would go as a classical particle through that path, he will be just destroyed. So there's, I don't know, a brick wall. So he can't get to these detectors. So photon that has never traveled this way brought us information that that passage is blocked.
Okay, so how the diagram will be look like then?
So
So am I right that if we have laser
yeah,
that reflects it and go down,
yeah,
it's 90 degrees as you mentioned.
yes, so 90 degrees.
So we have 90 degrees, then it's go right.
If
It's
it goes
180.
right, it just is still 90 degrees, so it just passed through. If it goes down, it gets plus 90 degrees, so it's 180. But it's
Okay.
not the problem of degrees like the problem of the absence of interference. So you don't have the something to interfere with because this path is blocked. And the thing is that this paradoxical situation, it looks like this because the wave function is defined in the whole space. So that's really, let's say, peculiar characteristic of the quantum mechanics. So if I define some system, a wave function for that system is basically defined for the whole universe we live in. And that brings this strange phenomena. So if I get photon here, I basically get information that this path is blocked without basically probing this path. So if I send a particle there, that particle, it will just disappear. But if the particles comes out here, I get this information. Well, one more interesting, let's say, thing. If you think that this sort of interference is something quite cumbersome, I could say that you probably have seen that previously. So if you have seen modern lenses, they have some violet bluish tint. So here is the photo of few lenses. You can see that. And this violet bluish tint comes from the so-called anti-reflective coating. And that coating is based on the same effect. So you have some sort of coating, and when light goes through, there is certain probability that it will be reflected from the glass back to the coating, and that it will be reflected from the coating. And you can find such materials and some method to do this coating so that light interferes destructively. And the probability of getting photon reflected is much smaller than the probability to get through. Well, that of course works for a certain wavelength. So for the white light that contains all wavelengths, you will get something in between. So some light will pass through, some light will be still reflected. But anyway, it is used in practice, and if you have if you all like to do photos, you can look at the lens, and now you will know that quantum effects are used to make it anti-reflective. Here is one more, let's say, thought experiment based on that interferometer of Mach Zehnder. It is called Elisur-Weidmann bomb tester, and it shows how paradoxical is the situation that we can get information that some path is blocked without sending a photon there. So here is the same Mach Zehnder interferometer, and here we are putting some sort of device. This device can be a bomb, if you send a photon, it detects photon and explodes. Or it can be not a bomb and it will just let the photon go through. And if you for some reason cannot distinguish between the bomb and not a bomb, you can use Mach-Vander interferometer to do that distinction. So you place it into one of the arms of that interferometer. So you see it here, and you are trying to detect photons in with these two detectors. And if you remember from the previous slide, if you get a photon on the detector that should be never ever activated if this path is free, you know that that is the bomb because the path is blocked, but at the same time you haven't sent a particle into that bomb, so it didn't explode. So you can get information that that's a bomb, but do not detonate it. Okay. One more experiment. It's called Stern-Gerlach experiment, and it demonstrated that there is some sort of magnetic properties to the particles, and that these magnetic properties, they quantize. We will call this property spin, and I guess we will talk a little bit about spins, because spin-spin interaction is basically what makes chemistry possible. So here is the device. You see electrons coming from some sort of slit, and you see here a magnet. This magnet creates a very strong, non-uniform magnetic field. And if you think about the particle like some sort, I don't know, some tiny compass needle, and if you have a very, very non-uniform magnetic field, you can think that it will drag that particle, well, depending on which way it is rotated, up or down. The interesting thing is the image that they have got. So here is their image. It's some sort of historical photo. Here is another view. I guess it's a little bit better, just because here we see that particles that are going through this device, it's, let's say, one slice through the middle of the device, and you can see that. Oh, I get one more comment. Oh yes, one more nice link. You can check that as well. So what we get here, you see that the image you get on screen, it basically, if you take this slice through the middle of the device, it will give you 2 points. So this means that the value of that magnetic property, it quantizes. So you don't get some sort of real number. It's not smeared, so you don't have a number of points. You get just 2 points. So it is quantized, and it has 2 values. We call it +1/2 and -1/2. What is interesting, that rotating this device, we still get these 2 points. So that gives us another interesting hint. It tells us that the particle can be in some sort of state that is a mixture of states, but okay, sorry, that is a mixture of states, and we will get that particle the exact state of the particle only when we measure it. So if we measure a particle state, we can get some information on it. Okay, how do I return a little bit back? Okay, so the key messages. So particles have certain internal property called spin. Spin is quantized, and particles, I didn't show that to you, but I wanted to know, they can be divided into 2 large groups, bosons and fermions. Bosons have integer spin, and example is a photon, and fermions have half integer spin, and examples are electron, proton, and neutron. So basically what we will be working with. Quantum measurement, it reduces the wave function into an eigenstate of measurement operator. I know that sounds a little bit complicated, but I guess I'll show you an experiment that does that, and it will be a little bit more clear. And we will deal almost exclusively with electrons, because chemistry is basically about transferring electrons here to there. And here is an experiment that I want you to see. Here you see two polarizers, and light is passing through these polarizers. So here you see two polarizers aligned, and here you see what happens if I rotate a polarizer. So what is happening here is basically the following. So we have light that comes, let me check some, take some another color. Here we have some light. It gets to the first polarizer. This polarizer is vertically oriented. So basically from when a photon comes to this polarizer and passes through, it makes something like measurement. So photon may come through this polarizer, or it may not. If it comes through, it means that the state of the photon is basically vertical. So let me draw it like this. If I have second polarizer that is oriented another way, so let's say this way, perpendicular to the first polarizer, this photon cannot pass through this polarizer, because when you take a projection of this vertical state on a horizontal state, you get zero, so you get nothing. Okay. Now let's think for a moment about quite an interesting thing. What will happen if I add one more polarizer? So I can add one more polarizer, and I can rotate it, let's say on the angle 45 degrees. Let me first show you what will happen if you place this polarizer in front of these polarizers and behind them. So you see that image gets just darker. Well, basically nothing interesting happened. But let's think about it. So light came to the polarizer that is polarizing diagonally. So let me draw it like this, it would be a bit easier. So it goes out in a state of diagonal polarization. Now it comes to the polarizer that polarizes that vertically. If it passes through, it will be polarized vertically. It comes to the next polarizer that is horizontal, and there is zero chance of passing through that polarizer. So we get dark image, so nothing interesting. Same thing if I put it in front. So nothing interesting, no light was coming through, so there's nothing to look for. But now, can you guess what happens if I place this polarizer in the middle between these two polarizers? So I get some light. Yes? Anyone ready to guess?
Obviously, the projection that would be 45 degrees straight, so there will be less energy, but it will pass through both polarizers.
Yes, absolutely correct. Okay, I hope everyone understands why that happens. So there is some smaller chance of passing, but there is some chance. It is non-zero.
Because it's not
like
the refraction effect. It essentially light still passes through in the same direction, because actually it's not like the direction changes. It's more like the phase inside the material it shifts to adjust for like interference.
You can
So
look at
yeah,
this state, this vertical state, as the result of interference of this state plus this state. And when you pass through the second polarizer, so one of them gets killed and one of them passes through. And
It's like as you mentioned in the slide when we have one blocked and
Yes.
another we have, so it's like 1 and a quarter chance it will have the possibility.
You can think about that wave function as a combination of like two functions, so a sum of something plus something, so nothing bad. Okay, so if we can predict that correctly, now let's look at the experiment. And here it comes. You see that? So right here. So let's check once again. So everything was dark. And now you see something behind. Yeah, so that's basically what I was drawing for you, so nothing special here. And now, with all that being said, I guess we are ready to get a little bit with all of our knowledge about quantum physics to atoms and to check what can atoms propose to us and what kind of quantum effects do we have there. So here's once again time-dependent Schrödinger equation. Here is a model of the hydrogen atom. So it's just a nucleus. It's well, it's not well written here. So hydrogen atom has one proton and nothing more. If you have deuterium, you can have one proton and one neutron. And sometimes deuterium is used in chemical experiments, so maybe we will meet that, not sure. And there is some sort of volume around the nucleus that is occupied, well, in case of hydrogen atom, with one electron. So we cannot draw electron exactly where it is, so that wouldn't be, let's say, quantum mechanical. But we can draw some sort of distribution of the probability where is it probable to find the electron, and you see that these distributions may be quite different. Okay, so what do they depend from? First of all, let's talk about so-called energy levels. So if we solve that Schrödinger equation, we will see that we can get a bunch of different solutions. That shouldn't be some sort of surprise for you that we can that from one equation we can get a lot of solutions. So the simplest case probably is quadratic equation. So you get two values of x. So in here you can get many different values for psi. And what's interesting, with each value of this wave function is associated a number that is basically energy. And here you see these energy levels drawn. So this is a diagram that shows them, well, maybe not to scale, but how do they look like. It is a traditionally to measure energy starting with E equals 0, and that is the highest energy level that you can occupy in atom. So if you have more than that, electron will just go away, so it will just fly away from the atom. And basically the difference between these energy levels gives you the amount of energy that you need to remove electron from one level and to put it to another one. So it's just the difference in energy that moves electrons. And we have a principal quantum number n, and different values for n. They divide orbitals into groups of similar energies called shells. So n defines shells. Numerical values for n are used in ordinary speech. So here you see that the lowest one has n equals 1, then n equals 2, 3, and so on. So the higher the n, the more energetical is the electron. And here is, let's say, experiment that shows us that electrons really have levels. So you see that if we give some energy to the atom, that can be done in different ways, and we look at its spectrum, we will see that the spectrum contains lines. So each of these lines corresponds to a certain energy. So you see that we don't have some, I don't know, some smeared spectrum, so it's not like any energy is possible. But you see that only certain values of energy are possible, and these discrete values are exhibited in a form of spectrum. So here you see different spectra for different elements, and you may see how nice do they look. And the color of gases that are used in, I don't know, in neon lights or some other lights, they basically depend on the emission spectrum of the appropriate gas. Okay, some more quantum numbers. We need to describe our electron. So the orbital angular momentum quantum number, or L, it determines the angular momentum of the electron as it moves in its orbital. This quantum number tells us the shape of the orbital. It can be, I will show you different shapes of the orbitals, and you will see that some of them are spherical, some of them are not. We'll be mostly concerned with S and P shapes. Here you see that that values L can take depend on the value of n. L can have value from 0 up to n minus 1, and the different possible values of L are given letters. And you see here that if you have n equals 1, there is only S angular momentum possible. If it equals 2, then S and P. 3, S, P, and D. So you can recall that from chemistry courses, this SPDF thing. I hope you know that. And magnetic quantum number, or ML, determines the spatial orientation of the angular momentum, and its value depends on the value of L, varying from minus L to plus L. Here are some examples. Most cases they are given, I know letters are given some suffixes. We'll be mostly concerned with S and P orbitals, so you will often see like px, py, pz, and s without any indices, because values there is only one value of L. Okay, and here it comes, orbitals. Here you see s orbital, p orbital, and d orbital. How do they look like in 3D? Here you see what happens when we change that value. So if you have px orbital, py orbital, and pz orbital. So here how they look like. And different shells, they have different capacity to contain electrons. And here I guess I have a link for you to show you some orbitals. Let's check it out. how that works for us. I hope it works. Yes, it somehow works. Okay. Here is some sort of example to show you orbitals and compare them. So here is 1s orbital. So it's just spherical, nothing interesting. If we have some higher energy, we may want to consider 2s orbital. Here it is. Same spherical, but bigger. So the bigger number, the bigger is the orbital. Okay, let's compare now p orbitals. So here is p orbital. You see here is let's say the probability of finding a particle is almost equal 0. So this is the orbital with one node. D orbital will have 2 nodes, and so on and so forth. So now you may recall that mechanical analogy with the rope I was showing to you, and here is basically that case with the rope having one node in the center. So here is almost 0 probability of finding electron, and here is some larger probability to find the electron. Colors show you, let's say, let's call them phases. I'm not sure if it's a correct technical term, but if we think once again about our rope analogy, so let me take some, this color, about rope analogy. So here is our node. So this is our node. It's here. Let's say this part is plus. So this is the part of the wave that is above x, and this part you can think of it like minus, because it's below. Of course, if you think about the rope that wobbles, you can think that these parts will swap places, but anyway, they will be, let's say, on different sides of this x-axis. So that's why it has some meaning to give them different colors. Yes, please.
So it's like the second video that you showed us where we have two like squares of web.
Yeah, absolutely correct. It's
Mhm.
exactly the same thing. Of course, that was some mechanical analogy, so it's a bit far-fetched, but it's pretty similar. So a node here, 0 probability of finding the particle, and some halfways on different sides of the x-axis. Okay, now let me find, how do I return back? Yes, I see one more question, please.
I mean, is it too early? Basically, I did not fully understand like how is angular momentum impacting this orbital.
You see that they have different shape. So let's return a little bit before. So you see that angular momentum tells us, do we have s or p or d orbital? And now please look at their shapes. So here is s orbital, here is p orbital, so some different angular momentum, and here is d orbital. So it basically defines for you the number of nodes that you will have.
Multiple, yeah. So in multiple dimensions. So
Well,
is that
it's
so?
in 3 dimensions, so you may have nodes. Yeah, some node may.
I mean, in multiple axes. So the
Yeah.
orbital is both in y and z, for example.
Yes, because 3 dimensions, so we have different nodes in different dimensions. Yeah, I see more questions. Yes, please.
Yeah, the question is about the orbital. If we compare about the video, so
Yes.
we watched about the orbital, or it was only about p orbital.
Well, I thought more about S and p orbital. Actually, that mechanical
So as it's the
analogy.
first video, p it was like the second video.
Yeah, and the third.
And D,
Well, yeah, maybe you can consider the third as
D if
some.
we have like two ropes.
No, you can think of it. You see what's the problem? That video is a mechanical analogy for 1 dimension, but we live in 3 dimensions. So if that rope was some sort of psi function defined on the x-axis, and that's all, it was just 1 dimension. So in our world, we should define psi function in all 3 dimensions. And I just cannot draw anything meaningful in 3 dimensions to show somehow all this moving. So you just need to take it with, let's say, a grain of salt, because it's just mechanical analogy, but the real world is a bit more, let's say, complicated. So yes, two nodes, that's d orbital, but since we are living in 3D, it will look much more complicated than just that thing in video. So you should take that into account. So so that's too bad, but we just cannot translate all the quantum mechanical things into, let's say, regular mechanic. The problem is that nobody actually understands quantum mechanics. You know that Richard Feynman once said that even he does not understand quantum mechanics, and for you to appreciate, he is the father of quantum electrodynamics, and he got Nobel Prize for that. So actually, if somebody could understand quantum mechanics, it was he. But even he told that, well, it's not. It's too strange.
Okay, one more question. Is it correctly remember S, P, and D, if we talk about chemical
Yeah.
or chemistry, it's like the level when we wrote something and we have the squares. We have one square, the next square, and the next square. It is that same
Yes, it's the
about
same thing, and
orbitals.
we will get into that just about in a moment. So here you see
Okay.
this image on the right. It's not squares, but I used just this sort of lines to show you that energy level, and with these arrows, we show the electrons that can live on that energy level. And I guess in the well, yes, in the very next slide, here it is, we get right to that. So the thing is that if we calculate all that stuff for the atom, we get different levels. And we have electrons. And these electrons should be placed on that energy levels. Well, just because these are levels calculated for them. And all atoms, well, as you know, the ball always goes downhill. So each atom wants to be in some sort of lowest possible energetical state. And how do we find this state? How do we distribute our electrons through these levels to get the lowest possible energy state? And we have few rules here that will help you. So the first one, Aufbau principle, or Madelung rule. The lowest energy orbitals fill up first. Well, pretty logical. If you want something the lowest energy, you should fill up the lowest energy orbitals first. And the order is 1s, 2s, 2p, 3s, 3p, 4s, 3d. Note that 4s orbital lies between 3p and 3d orbitals in energy. Pauli exclusion principle. So what I told you before, we divide all particles into two big groups, bosons and electrons. Bosons have nothing against being in one quantum state. Moreover, if you have ever heard about superfluidity or superconductivity, that's basically the effect when bosons come together in one quantum state and they move as, like, let's say one big particle, if I can say so. It's a bit far-fetched, but pretty okay. So maybe Bose-Einstein condensation. So that's the same thing. But we are in chemistry. We are mostly dealing with electrons, protons, and so on. Well, mostly electrons, and electrons are Fermi particles, and Fermi particles do not like being in one state. So this means that you cannot have two electrons in the same state. That leads to the principle called Pauli exclusion principle. So one orbital may occupy just two electrons, and only if they have opposite spin. So you must get at least some quantum number different, and when you are filling these levels, you can fill maximum two electrons at one level, and they should have opposite spin. And so-called Hund's rule. If two or more empty orbitals of equal energy are available, one electron occupies each with spins parallel until all orbitals are half full. So here's an example of that filling. For example, a hydrogen atom. We have one electron and we place it into the lowest possible orbital, 1s. Here is carbon. We will deal a lot with carbon. So placing these electrons, we have carbon has charge 6, so it has 6 electrons. We start filling orbitals from bottom to top. So we first fill 1s orbital, 2 electrons here. Then we have 2s orbital, 2 electrons here. and we still have 2 electrons, but on this state in 2 pi we have 3 possible orbitals, py, px, pz. So we use the Hund's rule and we put 1 electron into one, the 1 electron into another one, and this one is just empty. Here is the same example for phosphorus, but much more electrons here. Okay. Here is one more example, I guess, of filling electrons. So once again, hydrogen atom. So 2s, 2 pi orbitals for hydrogen are degenerate, so they are shown here at 1 energy level. Yes, please, I see a question.
Can you remind what is going to be after D? Because I remember some of them have more electrons, and when
F.
we fulfill all the atoms, yeah, F.
F.
So
F.
it's like 5D or 4D images.
I don't actually remember on my own, but F elements that get this F orbital is basically
Yeah.
lanthanoids and actinoids. So I don't think we will have to deal with them. Well, basically we will deal with just a small number of atoms that are used in organic chemistry and that so-called biogenic elements. So I guess I'll get to that in 1 or 2 slides, I guess. Okay, let's look once more at the electrons and the levels we have. So with the hydrogen atom, it has just 1 electron. Here it is represented as an arrow. It indicates electron spin. It can be either up or down, but here it is drawn up. And we see that it's placed on the lowest possible orbital. Here is boron atom. So atomic number 5. It comes before carbon. So carbon was 6, and here is boron is 5. Once again, we are filling 1s orbital. We can put here 2 electrons. Since its atomic number is 5, it has 5 electrons, so we should somehow put 5 electrons here and there. 2s comes next. Once again, we can fill it up with 2 electrons, and then we get to 2p, and we set 1 electron here. So nothing special. Here is nitrogen and oxygen atoms, and so nothing special. You just fill up these orbitals, and you follow that rules. We will be mostly concerned with so-called biogenic elements. It's carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. There are certain other elements that we will meet here and there, for example, as cofactors or signaling factors and so on, like sodium, potassium, calcium, magnesium, chlorine, and so on. There are certain microelements, I'm not sure, maybe we will meet them once again here and there as some sort of cofactors, but you can neglect them. So these biogenic elements, they have they are the most valuable for us, and we will mostly work with them. And just some terminology: the valence electrons are electrons in the outermost shell of an atom, and they can participate in the formation of chemical bond in the outermost if the outermost shell is not closed. So I will show you why that. Let me just check for a moment where are we in terms of lecture. Great. I suppose we can spend a little bit more time on the third-party resource. So here is the link for you. It's p-table. because this table is taking up too much. I will just show you how to use that.
But can you also send the link for this table,
It's in the
please?
slide, so I was just clicking link in the slides. So you can take in our Moodle, you can take my slides and find this link there. So how do I guess it works. Um, yes, so we may check a form of different orbitals by clicking here, and you see the 3D plot that we can rotate a little bit, and here you see the nodal plane. So yes, I guess just to get grasp of all these orbitals and how they are filled. The the second thing I want to show you already working in some sort of approximation. The thing is that all these orbitals, they were calculated for a hydrogen atom, and when we are using them for different atoms, it's a little bit stretched. They work pretty well, but you should know that here is some sort of approximation, and the real world may be a little bit different from what we calculate. For example, the rules I showed you, like Hund's rule and Aufbau principle and so on, they mostly work. So 99.9% cases they will work. So please look, here I have the 3D orbital is filled. So we have already half-filled orbital due to the Hund's rule. And now we are filling the spin-down electrons. So we are adding spin-down electrons to already present spin-up electrons. We go to nickel. So what do we expect? We expect adding one more electron. See that we have added this electron. So everything is okay. But here is an interesting case, copper. You see what changed?
So yeah, we have 4D elements. It's fulfilled the 4D element.
So we had to add one electron here, but when we go to at the cost of removing electron from here. Has 4s orbital field, so two electrons spin up, spin down. Copper should have been adding just one electron here and nothing more, spin down. But when I go to copper, s orbital, one electron is removed. This is one of the exceptions. There are not many exceptions. As far as I know, two, for example. So one is copper, the other one I forgot. Okay, I know one, but I know that there are at least two. But it's a really, really rare case. But what is instructive in this case, I want you just to remember that whatever we do, it's some sort of approximation. So we are already working in an approximation. So in some cases, this picture may a little bit break, or something like that happens, and that is pretty okay. So you should be ready for that, and do not expect it to work like mathematical theorems, but most of the time these principles will work and everything will be fine. But you just should be ready to meet some exception, and you should know that it may be, because the best result we can get is basically to solve the Schrodinger's equation, to solve it for all particles, and there will be one large wave function that describes the whole system, and that will be very complicated. Even numerical methods at the moment having some troubles with solving that equation. So so that may be. Okay, how much time do we have before first lecture ends?
10 minutes, up to 10 minutes.
So we have 4 minutes. Okay, I guess
Not
maybe
4,
if,
10. It's
10
7:30. The next one is
the
7:30.
next one starts. Okay, will we make a break in 10 minutes?
Okay.
I think yes.
Okay, then if you have maybe 1 or 2 questions, please. If not, let's take a break, and 7:30 we start. Yes, please.
So do I understand the concept of energy levels correctly? So the higher the energy level is, the less energy we need to apply to an atom to detach the electron from it, right?
Yes. So to detach an electron, let me find a picture here. So to remove an electron, he should surpass this upper level and fly away. So basically, the highest occupied energy level, there is some distance to 0. That's why we measure energy down into the minuses, and that basically describes how much energy you should apply to make this electron free and to let it fly away. So that's pretty it. Yes, I see some more questions, please.
Yeah, so I still have a question about the experiment with laser and the bomb.
Yes, please.
Wrap my head around it. Could you go back to the slide?
Yes, let me return back. One moment. I guess it's easier to get here. Okay.
So yeah, basically I understood the concept of angles and the probabilities, but I cannot comprehend how the bomb won't explode. It's like to get the 0 probability, we had to have like destructive waves, but that means that the particle should go like to the bomb, and it will.
You see, you have interference only if this upper path is unblocked. So if a photon can potentially go along this path, bad color, let me choose this one. If a photon can potentially go through this path, you get interference. So you add two waves or two wave functions for this path and for this path. But if this path, for some reason, is blocked, you don't have this wave. So you don't have to interfere with.
Yeah, but the first, the first splitter, no, it has a chance to go like
Yes,
to
it,
the
ha-
top,
it,
the
it has
bomb,
a chance to go here, to be stopped, and to never come out of the device. So there is
yeah,
50% chance it's pretty okay. If you put a
yeah,
bomb
and
here,
the bomb will explode.
yes,
No?
yes, if it will go to the bomb, it will explode. So there is a chance that you will explode the bomb. That's pretty okay, so
Okay.
50% chance. But there is 50% chance that it will go this way, and still 50%, that gives us 25%, that it will come out here. In this case, it does not touch the bomb. It does nothing
Yeah,
with it.
I understand. Yeah,
And
no,
yeah,
I
and that
understand.
brings you information that the second path is blocked. So that's it.
So basically, there is a chance, like 50-50, that I will explode, but a quarter
Yes,
to know that.
but in the
Yeah.
classical world, you had no chance to get a working bomb without exploding it. So you cannot not detonate the bomb and to know that it's real bomb. But in the quantum world, you can do that. Yes, I see more questions. Yes, please.
Yeah, the question is about like radiating system because you didn't mention the first. We saw it in syllabus, but can you just figure it out just to make it clear the I don't know, the amount of point it will have in which
You mean
way?
the grading system? Okay.
Yeah.
I think it's really good you mentioned that. Um, I think that at the end of each lecture, I will put some sort of homework for you. Something really simple. So I don't know, just sometime maybe 1, 2 questions, 3 questions. So no more. And I will expect you to do that in a week. So it basically is doable. I don't know, maybe in half an hour, but let's take a week. So maybe on the weekend or when you have time, so you can look at that. And then I will grade that, and I think the most of the grade will come from these homework. So I grade them 3 points for each homework. We will need to have
we saw it's like
some
45
midterms.
points we'll have.
Yeah, so we will need to have some sort of midterms. For the midterms, I will give you the same kind of problems, so really similar. So please, if you solve homeworks, keep the solutions. They will help you when we come to the midterm. At the midterm, I will give you 2 weeks. I will give you some larger set of problems, so it will be equivalent to the homework problems we did during 5 lectures. And a small task for an essay. So we will come to that. So really small task, and I will grade that that 2 things. So once again, 5 lectures. If 3 points, so 15 points for assignment, and I guess I set 10 points for essay, and that's basically that's it. Exam will be
also
at the end,
you
and
also
only 5 points for the exam, so I won't worry about that. So we will do some simple interview, and I guess if you perform well during the semester, that will be something really easy.
Yeah, I also put the additional task, so can you tell us what it's gonna be about?
I'm not sure at the moment, actually. So
Because it's like not required to pass, but it's 10 points, so it's interesting to have it extra points.
I will think about it maybe, because right now I'm creating this course on the go. So
Okay.
So yes, I think I will come up with something during the semester. So we have many lectures in front of us. Yes, I see more questions. Yes, please.
Okay, I wanted to ask, is there any possibility to take the exam in advance?
Yes, I guess, yes, I was told that if anyone has experience in biochemistry and bioorganic chemistry, we can make exam in advance. I'm not sure about the procedure, but I guess we can do some sort of interview, but I need some time to prepare on my own, and it will be okay. I'll I'll
Okay.
ask.
Can you approximate the date of this exam? Like, it will be this week or next week?
I'll maybe let's do it next week, I guess.
Okay, thank you.
Yes. Yes, please. More questions.
Do you have some list of literature for this course?
Yes, it was in the syllabus. There are a few books for this course, but I should warn you, they are quite voluminous. So I'm not sure if you can handle that in some reasonable amount of time. So for
Okay.
example, I take many things from Clyden. It's I guess almost 2,000 pages or something like that, and some other books in biochemistry, they are quite voluminous. So you can check syllabus. I have put some books into there, and I mostly take information from that books. But I should warn you, they are really voluminous. So yes, more questions, please. Okay.
I'm not sure if
Yes, please.
I will be able to ask. I honestly want to ask about like the impact of like the electron leaving the orbital. Why would like so on example of the copper atom, exactly as I would understand, basically atom like the electrons trying to fit in these different orbitals because of the rejection that they could guess. So why would an s orbital electron move upwards after receiving
Well,
electron?
yeah, I understand. Well, the thing is that the description in terms of orbitals is, as I told you, an approximation. So we took them basically solving a Schrödinger equation for a hydrogen atom, and it's really nice that they fit for for the most of other atoms. So we use them as some sort of, I don't know, basis. As we will see in the future, there are certain problems with this point of view, but it comes from the fact that we cannot solve the Schrödinger equation for many electrons that we have in many electronic atoms. So that's basically the problem we have.
And as I understand it, like, so if in the future, please, I would like really uh, grateful for like explanation why like the orbitals exactly impact like the reactions and
I guess we
yeah.
will get to that in our second lecture, because we will start talking about molecules and molecular orbitals, and how do they basically influence reactions. So it's not like we can understand everything, but there will be some things I want to show you. Yes, please, more questions.
So I want to ask, like, if we have an atom with two levels, like 1s and 2s,
Yes.
and we saw on the model that they look like spheres,
Yes.
and won't electrons inside those spheres interfere with each other?
Yes, they interact. That's true. If you calculate the Schrodinger's equation, you will put all the components of the energy, including Coulomb interaction between electrons. So that's really true. In some cases, we may neglect something. So if we are calculating, let's say, Schrodinger equation, or we are doing some approximation. So here we have positive charged kernel of the atom, and we have some electrons on the lower orbital. It's schematic view. And I have some electron on the higher orbital. Of course, it interacts with the electron, with the kernel, so that's okay. But since we cannot calculate precisely, in some cases we may say, let's do an approximation. And what will be an approximation in this case? We will say, let's treat the thing as one system that has charge one lower than it had, than just a kernel had. So it may be some sort of, you will see some sort of approximations when we neglect interaction between electrons, but in reality, in nature, they do interact. That's absolutely true.
Okay, so what I meant, it's like, can electrons from like second layer and the orbital, like from 2s, be inside like the sphere of 1s or not?
We will see, I guess. Well, there is a probability to find that electron anywhere. So basically, there is a probability that you find that electron, some very small probability that you find it in another room. So that's pretty okay. There's always some probability. Psi function is defined for the whole space. So whatever we have, psi function is defined there. What else? But we will see certain quite interesting phenomena. For example, I will show you so-called hybridization. It's when few electron orbitals interact and they mix up, creating something pretty new. And that will really make sense during certain chemical reactions and so on. So I will show you that during the second part of the lecture. Yes, I see one more question. Yes, please.
Yeah, there are actually two questions. So the first one, can you send the link for the presentation just for us? We can just look it through also at the same time as you. Just for us, it's gonna be easier. Yeah, and the second one, is I remember something about about this field. So when we have the electronics and when we draw this model, we have this sign of infinity. So we draw them as much as we have S or P model. So one, then we have one more infinity sign. Is that about something about low level?
I'm not sure actually. I'm not sure. So
it's like when we try to make a schematic I don't know, diagrams, not diagrams, but schematic view of the molecular. So after we find out how much S, how much P level we have, we can draw the level of electrons or whatever it can be. I don't remember. So it's like infinity.
Maybe you are talking about hybridization. So so hybridized orbitals, they have some form, something like this.
Yeah.
Maybe that's it. I think we will get to that in a moment. Yeah, I guess the second lecture has just started.
Yeah, okay, thank you so much for the link.